Hello everyone, this is Mrs. Lim. Welcome back to part 3 of pressure. Okay, in the previous few videos, we have covered about solid pressure and we have introduced the formula pressure equals to force over area. And in part 2 of the video, we have introduced to you about the hydraulic system, which also makes use of the formula pressure equals to force over area. Okay, in this third part of the video, we will be covering something new. Okay, we'll be covering how is the height of a column of liquid used to measure pressure. Okay, specifically, we'll zoom into the formula pressure equals to rho GH. Some of its application is in questions, as well as how do we use this height of a liquid column to measure atmospheric pressure using a barometer, as well as the use of a manometer to measure the pressure difference of a gas supply and the atmospheric pressure. Okay, so before we start, let's do some prior knowledge activation. So you have determined the contact area of a book resting on the table. So I'm interested in finding area. I give you the weight, which is the force of the book, as well as the pressure. So I know that I have a formula that links pressure, force, and area, which is pressure equals to force over area. So now I'm interested in finding area. So area is equals to force over pressure. So the force is 8 newtons divided by pressure 50. I get 0.16 and the units is in meter square, which is the SI units. So I need to convert that to cm square. So it will be 1600 cm squared. So the answer is D. Next, compared to wearing high heel shoes, wearing a pair of sports shoes will reduce the pressure on your soles. Explain this. So in this case, the difference between wearing a high heel shoes and a sports shoes is the area of contact with the ground. The force does not change because it's still the same person wearing the shoes. The force will be the weight of the person. So the weight of the person doesn't change, but the area changed and therefore the pressure changed. So the answer is D. A larger contact area between the soles and the ground is provided. Therefore, the pressure is much reduced. Next, okay, you need to understand that for liquid pressure, number one, the pressure will be the same at all points along the same horizontal level. So what do I mean by that? So if I have a bottled water and I were to poke holes, 3 different holes at the same level, you will see that the water sprays out at the same angle or sprays out by the same amount. Okay, this simply means that, okay, the pressure at the same depth is uniform. Okay, as long as you poke hole at the same depth, same height, the pressure at any point will be the same. Okay, so over here, you can see that if I were to pour liquid into this funny shaped tube, we have big cross-sectional area, thin cross-sectional area, slanted cross-sectional area, and beard shape. Okay, the liquid will always flow until the pressure is equalized. What do I mean by equalized? Okay, so I have point 1, 2, 3, 4. They are of the same depth. Okay, they have the same depth under the water. Okay, the liquid will always flow until the height of each of this tube will be the same, because the pressure at 1, 2, 3, 4 will be the same. Okay, because at the same depth, the pressure will be the same. And when I talk about that, I only talk about the vertical depth. I don't talk about the slanted depth or the weird shaped depth. Okay, next. So liquid will always settle at a common height. Okay, so you can feel the pressure as you dive down into a swimming pool. So the deeper you go, the depth of the water increases, and you will feel that the pressure increases on your eardrum. So the pressure in liquid increases with depth. Okay, you can see from this diagram over here, if I were to poke the holes at different height, okay, if the hose is poked at the top, you only have a small amount of depth above it. So the liquid pressure depends on everything that is on top of it. So for point number 1, the depth that's on top of it is only H1. So it only flows out by a small angle. Okay, but at point number 2, the depth is higher. The depth is greater. So the pressure is everything on top of it, which is H2, bigger than H1. And at 3, the pressure is everything on top of it, which is H3, which is the bigger. So it will shoot out the furthest. Okay, next. Okay, the pressure at a point within a liquid only depends on the depth. It is independent of the volume. the shape, the size, or the area of the container. So what do I mean by that? You can see from my diagram, I have three different containers with different cross-sectional area and holding different volumes of liquid. But if I were to make a hole at the same height, okay, and all these three liquids have the same depth of liquid at the top, okay, you will see that the water will shoot out by the same amount or at the same angle, okay, because it is irregardless of the shape or volume of the liquid. Okay, the force acting on the water at the same depth will be equal, will be the same. Okay, so again, this is the same like as what I mentioned before. The deeper the deeper the water, okay, or the increase in the depth of the water, everything that's on top of it, okay, the greater the pressure. So you can see this, which is what I mentioned just now. Liquid pressure increases with the height, and the height is everything above the point, okay, not below the point. Okay, that brings me to my formula. Pressure equals to rho GH, whereby H is the height in meters, rho is the density of the liquid, okay, and G, we can always assume it to be 10 unless the question otherwise state otherwise. Okay, so the pressure at a given depth beneath a liquid surface depends only on the depth, density, and gravitational field strength. But if we are using the same liquid, the density doesn't change. So the pressure at any point within the same liquid only depends on the depth. Okay, assuming that gravitational field strength doesn't change as well. Okay, so you can take a look at this diagram. A diver goes from a depth of 10 meters to 100 meters underwater. Assuming that the gravitational field strength is 10, density of seawater is about 1025 kg per meter cube. Determine the change in water pressure. Okay, so in such a question where there is no diagrams, the first step is always to draw a diagram to help you visualize. And when you draw a diagram, it's important to input important information. Okay, so in this case, I have a diver going from a depth of 10 meters to 100 meters. I use different colors to help me differentiate as well. So I draw my diver at 10 meters, which is the blue guy over here. Okay, and I label it, I'm at a depth of 10 meters. So this diver is going deep into the water. I become this red guy over here, which is 100 meters underwater. Okay, so I want to determine the change in the water pressure. I need to find the pressure at the start, at the blue guy over there, and the pressure at the red guy. Then I minus it away to determine the change in the water pressure. So I have a depth, H, and I give you the density. So you must immediately know that I need to link this to the formula, pressure equals to rho GH. So the first step, I find the pressure at 10 meters, the blue guy over there. I use rho GH, 10 meters times density times gravitational field strength 10. And next, I find the pressure at 100 meters. I'm also using rho GH, but now the H is 100 meters. I get the pressure. So I determine the change in pressure. I just minus them off. Okay, next, they say that glass tank used to construct large aquarium can be up to 5 meters deep. Explain why the glass is usually thicker at the bottom of the tank. So this one, again, they give you a depth of 5 meters. Okay, then they ask you why must the glass be thicker at the bottom? Okay, so you must immediately link to pressure equals to rho GH. The pressure of a liquid depends on the depth of the liquid. The deeper you go, okay, the more the pressure. Okay, the greater the height, the greater the pressure. So the answer is as follows. The pressure of water depends on the depth. The greater the depth, the higher the pressure. So the tank needs to be thicker at the bottom in order to withstand the high pressure. Otherwise, the glass at the bottom of the tank will break. Okay, next, we move on from liquid pressure into gas pressure. Okay, same like liquids. Okay, gas also exerts a pressure. Okay, that in the surrounding, there is a lot of gas molecules, or there's a layer of air, which we call atmosphere. And this atmosphere is actually caused by gravity pulling down on the air molecules. So gravity is pulling down all the air molecules, and therefore all these air molecules actually exerts a force over your body, the area. So you experience something called atmospheric pressure. The atmospheric pressure at sea level is about 1.013 times 10 to the power 5 Pascal. You don't need to memorize this number, okay, just for your general info, but no need to memorize. Usually the question will give you that. Okay. Sometimes we don't express it in Pascal. We just express it as this is 1 atmospheric pressure. In short, 1 ATM. Okay. So how do we know that there is atmospheric pressure? You may play the video. This is the YouTube link. You may play the video in yourself. Okay. So what happens is I'm just going to explain that atmospheric pressure is very powerful. This 1.013 times 10 to the power 5 Pascal is actually a lot. So what do I mean by a lot? Okay, you can see that over here, I have a wooden ruler. Okay, so normally, if I were to use my hand to in a fast motion to chop down this ruler would flip. Okay, there will be a turning effect. This ruler will flip and then it will drop off the table. But what happens if I were to put just a flat piece of newspaper, the bigger the better. Okay, a flat piece of newspaper covering this ruler on the table. And if I were to hit it hard, okay, at the ends, okay, this ruler will be able to break. What happens is, this is the power of atmospheric pressure. So there's a lot of air molecules acting down on the ruler. The purpose of adding the newspaper, the bigger the size of the newspaper, the better is, I want to increase the area, okay, of the atmospheric pressure. So if I have a piece of newspaper covering the ruler, all the air molecules are acting down on the newspaper, it will provide a force that is large enough for this part of the ruler, which is on the table, to stay on the table. Okay, because of the air molecule pushing down the newspaper pushing down on the ruler. So the part on the table, okay, the ruler will stay there. So when I exert a force downwards on this side of the ruler, the tip of the ruler, you will see that it will not turn. Instead, the ruler will break. So that's to show you how strong or how powerful is the force exerted by the atmosphere. Okay, so atmospheric pressure depends on the height as well. Okay, just like liquid level. So at sea level, the atmospheric pressure is about 1.013 times 10 to the power 5 Pascal. And then as you go up the mountain, there's lesser air. So when the air decreases, there's lesser molecules acting down on you, the atmospheric pressure decreases. Okay, similarly, if you go down underwater, okay, below sea level, then there is more air, more water acting on you, so the pressure increases with the depth as well. Okay, so how do we measure atmospheric pressure? We use a barometer. So how does a barometer works? I'll show you more in depth in the next picture, but over here you just roughly know what is made out of a barometer. So a barometer is made out of inverted glass tube. You just push this glass tube into the mercury, a basin of mercury over here. Okay, atmospheric pressure will be pushing down on this mercury level to push the liquid up into this glass tube. Okay, and then how does it work? Over here, you can see the first step, you need to know that when I put this inverted glass tube push this inverted glass tube into the mercury flow, number one thing is you need to know that there will be an empty space. The liquid level will rise because atmospheric is pushing the liquid up, but there will be an empty space at the top. This empty space is actually a vacuum. That means, this empty space is a vacuum. That means that there is no air particles at all. So if there's no air particles, there is no force exerted on point A. The pressure at point A is 0. Okay, nothing that's acting on it. Okay, and then what happens is you need to use your previous knowledge of liquid will always flow until the pressure is equalized. So the liquid will flow and settle at a common height. So what happens is, at this blue dot over here, okay, it's exposed to the atmosphere. The atmospheric pressure is pushing down on it, and molecules is pushing down on it, and then it push the liquid up, mercury liquid up to this height. Okay, you should know that at this common level, this red dotted line, the pressure at the blue dot will be the same as the pressure at the red dot. So the pressure at the blue dot is the atmospheric pressure. So how do I determine atmospheric pressure? It's the same as the pressure at point number 2, the red dot B. Okay, so what is the pressure at B? Is everything that's on top of it. So I have 0 pressure caused by the vacuum plus this height. Okay, this height, the pressure caused by this height of the mercury. Okay, so this height of the mercury is found to be usually atmospheric pressure at sea level is found to be about 760 mm of mercury or 76 cm of mercury. So I want to find the pressure in terms of Pascal. I need to use rho GH. Every time in terms of cm mercury, I need to use rho GH to find my Pascal. So 760 mm, I need to change to meter. So it's times 10 to the power minus 3. So 760 times 10 to the power minus 3 times density, 13,600 times G, 10. Okay, so I roll GH. Okay, so the atmospheric pressure is about 103 kilopascal. Okay, okay. Okay, next, let's zoom into more examples. Remember, I mentioned that the height is always the vertical height. Okay, pressure at any point depends on the height of the objects above it, the height of the liquid above it. Okay, so at pressure at point A, there is nothing on top, it's a vacuum. So the pressure at point A will be 0 mm of mercury. At point B, it will again be the vertical height. At point B, I have vacuum, nothing on top of it, plus 220 mm mercury. And at point C, it will be 220 plus 220, 440. And then at D and E, the pressure is the same because they're at the same level, which is also equivalent to the atmospheric pressure pushing down on it. Okay, so it will be 220 plus 220 plus 220, which is 660. Same for point D and E. Okay, remember we only look at what is on top of it. And then at F, I will have 660 plus another 300 mm. So I have 960 mm of mercury. Okay, more examples. Okay, just now it's in terms of mm of mercury. Now we can use in terms of cm mercury or in terms of Pascal. So at A, again, there is nothing on top of it. It's 0 cm mercury or 0 Pascal. At B, it will be everything that's on top of it. So it will be nothing plus this height H1, which is 96 minus 50, 46 cm mercury. Or I need to change it to Pascal, 0.46 meters. Okay, 0.46 meters. So I just use rho GH. Okay, same for C. C will be the same as atmospheric pressure, which is the same as the red dot over here. Same level, same pressure. So it'll be 96 minus 20, 76 cm of mercury. And I'll change it to Pascal. And at D, I will be 86, 76 plus another 10 cm, 86 cm of mercury. And then this will be in Pascal. Okay, next, you may scan the following QR code to investigate some of the factors that may affect the height of a liquid column of a barometer. Okay, we will investigate the following 3 items surrounding atmospheric pressure, the shape and size of the barometer tube, as well as the density of the liquid in the barometer tube. Okay. Okay, so if you have played with the simulation, you should have realized that the height of the liquid in the barometer, it only depends on the atmospheric pressure that is exposed to. So in atmospheric pressure is about approximately 76 cm of mercury. Okay, so you can see over here, I have many different glass tube. Some glass tube I push in further, some glass tube I push out further, some glass tube I tilt, some glass tube are fat, some glass tube are thin. But can you see that the height difference? Okay, the height of the mercury from the surface of the mercury throw, which is this dotted line over here, the height, okay, of the mercury is all 76 cm, which means the atmospheric pressure, which is equivalent to the atmospheric pressure. Okay, so if I were to bring this up on the mountain, you will see that the atmospheric pressure drops. Then it will no longer be 76. It might be 80 cm. No, it might be 70 cm or 60 cm mercury. And if I go bring it down deep underground, then it will be more than 76. The pressure will be higher. So it does not depend on the size, how deep the tube is placed into it. Okay, the vertical height always remains the same. Okay, which is 76 for atmospheric pressure. Okay, let's take a look at a few examples. What is the pressure on you if you dive to a depth of 5 meters underwater? Assuming that the atmospheric pressure at the surface of the water is 101 times 10 to the power 5. Okay, and they give you the density and gravitational field strength. So again, there is no diagram. It would be good if you could draw a diagram. So I will go and draw a diagram. Okay, so you are at the bottom. Okay, and you have a depth of 5 meters of water. And over here, there is an atmospheric pressure acting on you. Okay, which they give you is 1.01 times 10 to the power 5 Pascal. Okay, they want you to calculate what is the pressure on this diver or on you. Okay, so the pressure depends on everything that is on top of you. So you have atmospheric plus that 5 meters. Okay, that 5 meters of water. So atmospheric pressure you can sub in is 1.01 times 10 to the power 5 plus that 5 meters of water. You need to use the formula rho GH to find it in Pascal. So it's 5 times density of water, 1000 times G, 10. Okay, you get this amount. So this is the total pressure acting on you. Next, okay, in a simple barometer that measures the atmospheric pressure, the mercury column is measured at 760 mm at sea level. Okay, this is the normal case. The atmospheric pressure is 760 mm of mercury. But now some air is being introduced into the vacuum at the top of the mercury column. So now there is some air. With air, okay, it is going to exert some force on this mercury column. So the air will push down on this mercury column. So this mercury column will no longer be 760. So explain how this will affect the mercury column. With air being introduced, the air will exert a downwards pressure on the mercury column. So the mercury column in the tube will, the height of the mercury column in the tube will decrease. Okay, so now the new height becomes 500. So they want you to determine what is the pressure of the air inside. Okay, so I'm going to make some markings over here. Okay, so originally it's 760, but now I'm left with 500 mm. You know that the pressure at outside, the atmospheric pressure, is the same as the pressure at here, is the same as the pressure. The 3 red dots will have the same pressure. So the outside atmospheric pressure is 760 mm. Here is 760 mm. So inside that red dot must also be 760 mm. So if my height of my liquid column is only 500, I need to have some pressure here. This pressure will be caused by the air. Okay, the air must be exerting and pressure equals to 760 minus 500, which is 260 mm. So everything that's on top of it will be pressure of air, 260 plus 500, you get 760 mm, which is equivalent to the one at the outside, the atmospheric pressure 760. So this is how you solve questions. Okay, you can take a look at the answer. Pressure in the space above the mercury column no longer zero. There will be some pressure. Okay, so the height of the mercury column will fall because there's air pushing down on the mercury column. So that air pressure will be 760 minus 500, which is 260 mm of mercury. Okay, next, why is water not used in a barometer? That leads to my point of density. Okay, the difference between mercury and water is the density is very much different. For mercury, the density is about 13,600. For water is 1,000. So mercury is about 13,000 times more dense than water. Okay, so why is this so? So you can take a look at the work example. Mercury, 13,600 for density, replaced with water, which has a density of 1,000. What is the height if I were to use it with water? Okay, for mercury is 760 mm. So now what is the height if I were to change it to water? Okay, so what happens is you should know that the atmospheric pressure will be the same. So if I were to use mercury, I get 0.76 times 13,600 times 10 will be equivalent to, I don't know what's the height, times 1,000 times 10. Okay, so you can find the height of the water will be 10.3 meters. So you don't have such a long tube that can accommodate 10.3 meters of water. So that's why we don't use a water barometer. we use mercury, which is the densest liquid. The more dense the liquid is, the lower the height. Because, okay, let me give you the formula. Pressure equals to rho GH. And the density increase, like mercury, I have a very, very high density. For the same pressure, same atmospheric pressure, my height will be reduced. So I have a small height, which is 76 cm. But if I were to use water, my density is very, very low. Okay, so if my density is very low, this is going green one. If my density is very low, pressure remains the same outside, then this height must increase. Now my height will be 10.3 meters. Okay, it's too high. Okay, so the height of the water column in the barometer will be 10.3 meters in this case. Okay, I will stop for this part.